We often look for oxygen as a biosignature. Now, why do we do that? Does life really need oxygen to survive? In today's video, we're going to talk about the hallmarks of what an organism needs in an energy source. In order to understand these principles, you must have a strong working knowledge of redox chemistry and electrochemistry. So I've linked a few review videos below. So go back and brush up on any concepts you don't feel comfortable with before continuing with this video. When I'm doing science outreach, I often ask people what sources of energy power life on Earth. The first answer I usually get is the sun, but when I push them further, people come up with hydrothermal or volcanic energy. These sources of energy are important, but not for the reasons that people think. So we're going to talk later about where these play into the energy system here on Earth. For now, though, let's think about the chemistry that actually powers a lot of life on Earth. So if you remember, a redox reaction is a two-part reaction in which one substance loses an electron and the other substance gains that electron. When people talk about redox reactions and electrochemistry, they often talk about batteries. That's not too surprising because every electron transfer has an associated energy. You may remember this equation from general chemistry. Delta G equals negative NFE. As a quick reminder, delta G is the Gibbs free energy of a reaction, which is basically the maximum amount of work you can get out of that reaction. N is the number of electrons exchanged in that balanced redox reaction, F is the Faraday constant, and E is the cell potential. Now, when you think of cell potential in a galvanic cell like this battery, you think about the two half reactions. One will be the anode or oxidation reaction, and the other is the cathode or reduction reaction. When we are talking about life, we don't always use the terms oxidation and reduction, even though those are the processes that are happening. Instead, we tend to use the terms electron donor and electron acceptor. Now, a lot of books will show you a picture of something they call a redox ladder, and that may look something like this. You can see that each of these possible reactions has an associated E0 value, as well as an associated number of electrons. Now, as you look at this redox ladder, you may notice a couple of things. First, you have two chemical species in each box, one on top and one on bottom. The one on top is going to be the reactant, while the one on bottom will be the product of that reaction. Secondly, you will notice that these reactions are not balanced half reactions, so you will have to balance them at some point. Finally, you'll notice that these reactions are arranged according to their E0 value. In this particular redox ladder, the highest value is 1.23 volts for the reaction that turns oxygen into water, while the lowest value is for turning iron 2+ into metallic iron. So if you remember what these E0 values mean, you might ask how anything can use iron 2+ for energy when a negative E0 value represents a non-spontaneous reaction. So it's important to keep in mind that all of these are half reactions. In fact, all of these are reduction half reactions. So the species on top will be an electron acceptor. What is the electron donor in this case? We often use this generic reaction of CO2 turning into CH2O. Now, biochemists tend to use CH2O as shorthand for any carbohydrate. I've written the reaction here as it might look if it were in the redox ladder, but let's actually go through and write a balanced redox equation for a couple of energy possibilities in our redox ladder. I'm going to start with the iron 2 reaction since it didn't seem like that would be spontaneous. So we're going to use it in conjunction with a balanced carbohydrate reaction. If you look at the E0 values for these two half reactions, you see that the carbohydrate reaction has a much smaller potential. That means that it's going to be the oxidation reaction. And because it's the oxidation reaction, it's losing electrons. So this reaction, as it's written here, is actually going to run in reverse. Oh, let's flip it around. Okay, the next thing we need to do is figure out how many electrons will be exchanged in the balanced reaction. The bottom reaction has 4 electrons, while the top reaction only has 2, and we need those numbers to be equal. So we're going to multiply the top reaction by 2 in order to get equal numbers of electrons in each half reaction. So now that we've multiplied it by 2, let's go ahead and add these 2 reactions together, and then we can cross out anything that appears on both sides. In this case, that's only the electrons. So here is our final reaction, and now let's calculate the cell potential for this balanced reaction. Remember that the cell potential will be the E0 value for the reduction reaction minus the E0 value for the oxidation reaction. So that's going to be negative 0.44 minus negative 0.71, which gives us an overall E0 value of 0.27 volts. So you can see that even though the reduction reaction had a negative E0, the oxidation reaction had a much more negative E0, and therefore we will have a spontaneous reaction. Let's try that again, only this time let's use the reaction of oxygen turning into water. So here's the balanced half reaction for oxygen, and once again we see that the carbohydrate reaction is going to be the oxidation reaction because it has a smaller E0 value. So again, we flip it around. This time we have the same number of electrons in each half reaction, so we don't need to multiply anything. We can just add them together as they are. Once we do that, we can again cancel out anything that appears on both sides of the equation. Not only can we cancel out the electrons this time, we can also cancel the hydrogen ions, as well as 1 water molecule on each side. So again, here we have our final balanced reaction, and we can calculate our E0 value. We have 1.23 minus negative 0.71, which gives us an E0 value of 1.94 volts. So you can see that this is much larger than the value we calculated for the iron reduction. It's 7 times larger. Here on Earth, we know that a lot of organisms rely on oxygen as part of their energy production. There are many organisms that use alternate electron acceptors, but they're all single-cell organisms, bacteria and archaea. And that's because it's a lot easier to power a large organism with something that produces more energy. So if you look at where we find organisms that use these alternative energy mechanisms, it tends to be in anoxic environments, underwater, underground, etc. That's because organisms usually use the most energetically favorable energy source available. Which makes sense, because if they do that, organisms don't have to expend a lot of energy just trying to find their energy source. So up till now we've been using E0 values, but remember that the little superscripted 0 represents what happens under standard conditions. So that would be 25 Celsius, 1 bar pressure, and 1 molar concentration. But most reactions don't happen under standard conditions. So this is where we bring in the Nernst equation. Remember that the Nernst equation finds the cell potential under non-standard conditions. Basically, we're going to adjust the E0 value with this second term, which includes a lot of different factors. So let's lay out an example. How could we calculate the actual cell potential for the transfer of electrons from carbohydrate to oxygen? First, let's figure out what our Q expression is. This is basically going to be the concentrations of the products divided by the concentrations of the reactants, just like you did with equilibrium constants. And if you have coefficients, make sure you put those in as superscripts. So now we can plug that in for Q. And we've also calculated our E0 value, so we can plug that in. And because we've balanced our reaction, we know that the number of electrons that's exchanged is 4. That's N. What's left? Our temperature in Kelvin plus 2 constants. So obviously the value that you will get for E here is going to depend on things like your oxygen concentration. If you're at high altitude where there's less oxygen, you will get less energy out of this reaction. So when we think about environments and what energy is available, we not only have to think about what's there, but also how much there is. All right, now we're going to talk about an important factor in energy production. To make energy, we breathe in oxygen and we breathe out water vapor. Now, obviously, we also have to have carbohydrates or some similar electron donor to make this work, but we're just going to ignore that for now. If this was the only thing that happened, at some point the Earth would run out of oxygen because it would all have been turned into water. But that doesn't happen, because there's another process that turns water into oxygen. That process that we call photosynthesis is basically the reverse reaction of respiration. And because it's a reverse reaction, it needs exactly the opposite amount of energy to make it run. So if we get 328.1 kilojoules per mole from respiration, that means it requires an input of 328.1 kilojoules per mole to cycle that water back to oxygen. So this is an important process that we call nutrient cycling. The basic idea is this: whatever you use for a process has to be regenerated somehow. If that process is a spontaneous one, the regeneration will happen via a non-spontaneous process and will require an energy input, like the sun, like hydrothermal or volcanic energy, and that's where those come in. This concept of nutrient cycling applies to everything, not just stuff related to energy production. So I showed the oxygen-water cycle, but we could easily also show a carbon cycle where plants take in carbon dioxide and output carbs, and then we take in carbs and output CO2. We could do nitrogen cycling, etc., etc. So now let's take the principles that we've learned and apply them to a world that is not Earth. This is Europa, a moon of Jupiter. Now, we know that Europa has a liquid water ocean beneath its icy surface. We also know that Europa is too far from the sun to make much photosynthesis possible. Besides, the water exists under several kilometers of ice, down where the sun don't shine. Many people talk about hydrothermal vents on Europa as a source of electron acceptors, but I've just told you that those don't produce as much energy as oxygen would. So, is it possible to have oxygen cycling without photosynthesis? I and many other scientists believe that it is. So this is how it would work. Jupiter has a really intense magnetic field, 20,000 times stronger than that of Earth. Just like on Earth, charged particles get caught in the magnetic field. And so Europa, which lies inside the magnetic field, is hit with a constant stream of charged particles. And these charged particles turn water in the ice shell into hydrogen peroxide. Where there is a lot of hydrogen peroxide present, it can react with itself to turn into oxygen and water. So here's what we speculate an oxygen-based ecosystem might look like on Europa. Let's say we have organisms that respire oxygen for energy production and output water. That water can then be hit with those charged particles from the magnetic field and turned into hydrogen peroxide, which then turns into oxygen. One model estimates that there's enough oxygen put into Europa's ocean to support 1 to 3 billion tons of fish. Now, that's not a lot compared to Earth's ocean, but it is something. So when you're examining an environment for possible energy sources, the first thing you want to do is to look for some sort of redox disequilibrium, or hopefully more than one. And then you need to see if there's any way that your electron acceptors and electron donors can cycle back to keep the ecosystem running. I hope this was helpful, and I look forward to seeing you again soon.